A great performance has a quality we recognize but can't define. A spirit, a kind of magic. The most important thing that happens in the recording process is trying to preserve that magic. A microphone picks up a performer's vibrations, in a sense, their soul. Think of the microphone as the all-important first link in the chain, the mirror that captures and reflects that magic.
Microphones were one of the first things that had to be perfected to achieve better sound transmission. In the 1920s and 1930s, microphone manufacturers tried all sorts of shapes and sizes and designs, struggling to increase the frequency range or sensitivity of their microphones. This is the Western Electric 618, which was made about 1930. It was the first microphone to break the 10,000 cycle barrier. That was hot stuff at the time. Now, in those early days, the people who made microphones were big communication companies like Western Electric, Bell Labs, and RCA.
In the 30s, RCA brought out the first microphones to be widely used in the developing radio and film industries, the RCA 44 and 77 ribbon microphones. This is an RCA 44. By the 1940s, RCA ribbons had pushed the frequency range to around 16,000 cycles. By then, many small companies in the U.S. and overseas had begun to design and market all types of microphones. Today, there are hundreds of models of microphones. While microphones in general have been continually improving, one cannot assume that each new model by a particular manufacturer is an improvement over the previous one. Some early models are exceptional and always have been, while some of their successors just don't measure up. Some mics have gained a reputation that when you sing in them or play into them, it feels like you're on a cloud, surrounded by an aura, like you're wearing golden slippers. These great microphones somehow capture that elusive quality that lets a singer or musician hear the way they've always wanted to sound. It becomes their sound. What's the golden slippers for any given person? For some, it's an old, rare condenser tube microphone, while others prefer a current model. Every singer's golden slippers vary somewhat with who they are and how they hear themselves. But the best mic can only pick up what's coming into it. If the sound in space is lousy, no microphone can fix it. On the other hand, a good sound through a junk mic can't be fixed with EQ. I think it was Ben Franklin, who said a sow's ear doesn't hear so good. Well, Ben didn't make many records, so we won't talk about that. In this tape, we will begin by looking at how microphones work and how the variables of size and mass and pickup pattern affect a mic's sound. This will help you to develop a feel for how to choose the right mic for each situation. Then we'll look at how to set up microphones and how to get the best possible sound in your situation. Finally, we will look at strategies for miking a variety of specific instruments. Let's look inside a typical dynamic microphone. Inside is a diaphragm, like the diaphragm inside a human ear. As you can see, it moves freely in response to pressure. Like a weatherman's barometer, the diaphragm responds to slight atmospheric pressure changes on its surface. Obviously, a microphone, like our eardrum, is significantly more sensitive in its ability to pick up slight and rapid atmospheric changes. That's why mics will respond if wind blows across them. In a sense, a microphone is the wizard's wand that captures the wind and holds the magic. Once captured, we can change it, transform it, then relive that magic moment over and over again. Because the diaphragm is responding to net atmospheric pressure changes on its surface,
There are some laws of physics which apply to its mass and diameter. If the diaphragm diameter is not sufficiently small, high-frequency sound waves with very short wavelength will present offsetting pressures on the surface of the diaphragm. If there is equal but opposite wave pressure across the surface, the result will be no net movement, so no output will be generated. This is called acoustic phase cancellation. Now, in reality, no sound wave is perfectly symmetrical, so cancellation is never complete or total. However, a general principle of microphone design is that the smaller the diameter of the diaphragm, the better the high-frequency response. For instance, if a 1,000-cycle wave is about a foot long, and a 10,000-cycle wave is a little over an inch long, a 20,000-cycle wave is a little over a half inch. There are many capsule diaphragms that are about that big, and a few that are larger. This causes them to have an uneven high-frequency response. For example, this microphone has a very large diaphragm, and this mic has a small diaphragm. Let's compare their response to a high-frequency signal. As you can hear, the smaller diaphragm has a much better high-frequency response. On the other hand, a little tiny diaphragm will not be that good at low frequency. Since the diaphragm responds to net atmospheric change at any given instant, there will be very little physical movement as the long, low-frequency waves pass by the capsule. A larger diameter gives much better response to the very long waves produced by lower frequency. So a small diaphragm is generally brighter and more brilliant for recording upper register sounds, and a larger diaphragm is richer for recording low register sounds. The other key variable affecting the performance of a diaphragm is its mass. Heavier diaphragms, or diaphragms attached to a heavy coil, are less able to respond to very quick atmospheric changes. The laws of physics say a larger mass requires more time to get going. And then inertia comes into play, making it harder to slow down and change its direction. This microphone is light and compliant and responds quickly and crisply to the sound of the kick drum. This 4-inch speaker can also be used as a microphone, but its mass is extremely high. It's not very responsive to high frequencies or transients. A transient is the leading edge and initial attack of the sound envelope. A transient generally begins the sound event, for instance, the crack of the snare. If a microphone does not have a good transient response, then the sound which it reproduces will have less attack and percussiveness. Let's take a look at this. The lighter and more compliant the microphone, the better its transient response. Mics with bad transient response will lack clarity no matter how much you boost the treble. Let's review the ways in which the characteristics of the diaphragm affect the sensitivity of the microphone. The diameter of the diaphragm affects frequency response. A small diameter diaphragm will be more sensitive to high frequencies. And a large diameter diaphragm will respond well to low frequencies. The mass, or weight, of the diaphragm affects the speed with which a mic responds to a sound. The lighter the diaphragm, the faster the response. Once the acoustic sound pushes or pulls the diaphragm, this motion must be converted into an electron flow. Most microphones use one of two different transducer principles. The first group uses magnets and generates a signal
through the vibration of a conductor in a magnetic field. These include moving coil, ribbon, or regulated phase designs.
Moving coil, or dynamic microphones, are designed along the lines of a speaker. A moving coil microphone has a spooled coil connected to its diaphragm, usually at the back. The coil sits inside of a circularly channeled magnet. As the diaphragm moves inward, the coil breaks magnetic lines of force spanning the gap in the magnet, and a current is generated in the winding. When the diaphragm moves outward, the magnetic lines of force are broken from the opposite direction, and the flow of current in the coil is also reversed. The oscillating voltage electrically shadows the acoustic sound. How often the diaphragm changes direction reflects the frequency or pitch. How far the diaphragm travels in a given instant reflects the loudness of the sound and determines how great the output voltage will be during that instant.
Generally, as a group, moving coil microphones have the greatest amount of mass, although every model has a different compliance. Variable factors include the diaphragm material, its thickness, how it's hinged so that it can move, the size and weight of the coil, and so on.
Ribbon mics also use magnetic principles. However, in their case, the diaphragm is also the electrical conductor which breaks the lines of force in the magnetic field. The classic RCA 44s and 77s used long, thin ribbons of corrugated metal. The ribbon is held at its ends and positioned between two magnets of opposing polarity. As it vibrates back and forth in the magnetic field, current is generated in the ribbon diaphragm.
A ribbon mic has much less mass than a moving coil, and therefore is much more compliant and generally responds to percussive sounds more quickly. It will also have good high-frequency response depending on the length of the ribbon, but it's traditionally been more fragile. If the microphone was hit with a high-velocity pressure wave, it could stretch or snap the long, thin ribbon. So RCA 44s and 77s are not good choices for kick drum mics. However, in recent years, some manufacturers have developed ribbon technology to the point where they are reasonably durable, such as this Bayer M130, which can be used even on drums.
The regulated phase microphone also uses magnetic principles. It has the durability of the moving coil with the compliance of the ribbon. They attach or print a spiral coil right on the diaphragm's flat circular surface. The round diaphragm is held in place between two disc-shaped magnets, which are full of holes and acoustically transparent to let the sound pass through.
Because the diaphragm has its windings suspended between two magnets of opposing polarity, its output is generated like a ribbon. But because it's held in place along its entire circumference, it is as durable as a moving coil. The response is exceptionally compliant and very sensitive with good output and transient response. At screaming loud output levels, it's flatter with less distortion than a moving coil or a ribbon, and for that matter, most condensers.
The second basic type of microphone, the condenser mic, uses capacitive rather than magnetic principles. A capacitor is a storage device for electrons. It usually consists of two closely spaced metal plates with a thin insulator or dielectric between them. If the relationships are fixed between the various parts, the amount of storage or charge is also fixed. In a condenser mic, the rear plate is fixed, but the front is a movable diaphragm with a very thin surface coating of metal, usually silver. As this diaphragm vibrates in response to sound waves, the varying distances between the plates change the electron storage capacity of the capacitor. Electronic circuits sense this change and amplify it to a usable level. Condenser microphones come in all sizes, price ranges, and qualities. They have traditionally been used mostly in studios, while dynamic microphones have usually been used with PAs. However, over the last few years, more and more condenser mics are built roadworthy.
In general, condenser microphones are the most compliant type of microphone because their mass is so small. Ribbons and regulated phase microphones are nearly as compliant, and dynamic microphones have the greatest mass and are the least responsive, though there are a few dynamics which are fairly bright with reasonably good transient response. One more thing about condenser microphones, unlike magnet-based microphones, they always need a power source and have an internal preamplifier. Even if the capsule has a so-called permanent charge, the mic will still need either an internal battery or an external power supply, commonly called phantom power, to provide power to the preamplifier in the microphone. Phantom power is a way of providing a DC voltage, usually 48 volts, from the console, or a power supply, to the microphone. It uses the same balanced wires that are taking the sound back to the console. The AC audio is going in one direction and the DC in the other at the same time and down the same wires. Phantom power is only used on condenser microphones. In fact, if it's used on magnetic-type microphones, it can make them sound funny and possibly permanently change their characteristics.
We've looked at 4 basic types of microphones. All 4 types use a pressure-sensitive diaphragm to cause a fluctuating voltage. In the heavy but durable dynamic microphone, the vibrating diaphragm moves a coil in a magnetic field, creating a fluctuating voltage in the coil. In the light but delicate ribbon microphone, a thin metal ribbon vibrates inside the magnetic field, creating a fluctuating voltage on the ribbon itself. The regulated phase mic combines these 2 approaches with a spiral coil printed right onto the surface of the diaphragm. Finally, in a condenser mic, the movement of the diaphragm causes fluctuations in the storage capacity of a capacitor. Condensers are generally the most compliant of mics, but they do require a power supply and internal amplifier.
A pickup pattern, or polar pattern, describes the directional characteristic of a microphone. More than anything else, it's the microphone's housing design that determines its directionality. Any of the capsule types can be made to have various directional characteristics. Most mics have only one pattern, but some are selectable or interchangeable. There are 3 basic patterns: omni, figure 8, and cardioid. Now, if you build a box around a diaphragm so that the back of it is not exposed to the environment, then the front of the microphone will respond equally to passing sound waves from all directions. This pattern will be omnidirectional, or spherical. Regardless of where the sound is coming from, the microphone will respond to changing atmospheric pressures on the front surface of the diaphragm. As you can hear, the response of this ATM-10 Omni microphone remains fairly constant as it rotates in relation to my voice. Sometimes there's a little bit of a high-frequency dip at the back of an Omni because the microphone's body is somewhat blocking the very short high-frequency wavelengths. However, by and large, the microphone has a spherical pickup pattern. When both sides of the diaphragm are exposed, sound that arrives from the front and back, or on axis, will pick up normally. But sound arriving from either side will create an equal but opposite pressure on the diaphragm, resulting in no net movement, so no output is generated. This describes a bidirectional or figure 8 pattern. When I speak into the front of this bidirectional microphone, you can hear a full response. Now listen to what happens as it rotates. As I face the side of the mic, my voice strikes the diaphragm with equal intensity at both sides, so my voice cancels out. But the response to the back side of the mic is just as strong as the response to the front. Ribbon microphones are particularly suited for bidirectional operation, while moving coil mics have seldom been. A 3rd type of pickup pattern is called cardioid. Cardioid mics are directional mics that will, to varying degrees, pick up sound in front of them while rejecting sound coming from behind them. They're able to do this by the use of ports, which are common to all cardioid microphones. The ports are openings behind the capsule, which on some models extend all the way back along the body of the mic.
The ports are acoustic labyrinths, or paths, for sound to reach the back of the diaphragm. A given instant of sound pressure from the rear enters the ports as well as continuing on to the front of the mic. The labyrinth delays the signal by half a wavelength.
When it reaches the diaphragm, the sound that enters the port provides an equal but opposite pressure to that on the front of the diaphragm. There is little net movement or output. Listen to what happens as this cardioid mic is rotated. Notice that as my voice moves behind the mic, it starts to lose clarity and brilliance and sounds off mic. As it continues around, the clarity returns. The basic cardioid pickup pattern is heart-shaped. 3 increasingly directional cardioid variations are the super, hyper, and shotgun patterns. When you're in close proximity to a cardioid microphone that has ports, you tend to have a lot of proximity. Proximity is when the low-frequency sounds in your voice get louder when you crowd the microphone. Since my baby left me. The port lengths reinforce these lower waves when you get very close to the microphone. That's why on some PA microphones, the low frequencies go way up when you eat the mic. Proximity can be a good thing as long as you're aware of what's going on. A lot of engineers, including myself, like to use a mic with a fair amount of proximity for recording tom-toms and other drums. Getting the mic right up against the drum tends to give it more power, more bass. Similarly, sticking a mic right up against a guitar amp speaker cone will do the same thing. Many studio microphones have very elongated ports along their bodies. If that type of microphone is not put into its holder correctly, the clip can block the ports and cause the mic to lose pattern performance. I've seen unaware roadies tape up the mic with numbers and block the ports, or somebody holds the mic and blocks the ports with their hands. In either case, the pattern will have changed. So make sure you don't tape up the ports, and if you're going to use a handheld mic, make sure it's one that doesn't have ports along the body. When you're looking at the specs of a cardioid mic, you need to look at more than the on-axis frequency response. You also need to check the off-axis coloration, which describes the frequency response in relationship to the polar patterns of the microphone. In other words, what does the microphone pick up in its off-axis area? We're feeding white noise through this speaker to a cardioid mic. You can see on the spectrum analyzer that as the mic rotates off-axis, the highs drop away, but the mic continues to pick up plenty of low frequency. Many cardioid microphones are directional at high frequency, but relatively non-directional at low frequencies, so you're likely to pick up tons of low-frequency rumble from everywhere. That's why I tend to prefer doing vocals on a bidirectional mic. Even though I may only have one singer standing on one side of the mic, what ambience or leakage I have is full range and not just gobs of low-frequency rumble. Both sides are live, with the capsule facing away from the singer, picking up some room sound, which I tend to want a little bit of anyway. The sound I do get, though, has very little off-axis coloration. We've looked at 3 basic pickup patterns, all fundamentally determined by the shape of the microphone's housing. The omnidirectional responds equally to sound from all directions. The bidirectional mic responds to sound from front and back, and sound coming from the side is canceled out. With cardioid mics, you have a wide range of possible pickup patterns, but you have to be careful to keep the ports unobstructed and to watch out for proximity and off-axis coloration. Oh, I almost forgot. The 4th pickup pattern is the one you use after the gig when you're trying to get to know somebody that's been watching you play, but that's a whole other story. There are 2 additional factors we need to consider, which become especially important as soon as we start using more than one microphone. These factors are polarity and comb filtering. Now, both involve a phenomenon called phase cancellation. At its most practical, polarity has to do with how the mic leads are soldered to the connectors. Normally, a positive-going acoustic event should generate a positive-going electrical pulse.
But by taking the wires coming out of the capsule and reversing them at the connector, a positive acoustic event will now create a negative going electrical pulse. The capsule is now out of phase by 180 degrees, and its polarity has been reversed compared to the acoustic event.
It is essential to know that the polarity of all your mics is correct and the same. If one or more of the mics is reversed compared to the others, it will sound subtly different because, for instance, the speaker will move away from you when the kick drum's head and sound comes towards you. If two mics are on the same sound and they're out of phase with each other, when their outputs are combined to mono, there will be phase cancellation on that common sound.
The best way to make sure that all your microphones have the same polarity is first to make sure your mic cables and speaker wires are correctly hooked up. Then plug in one cardioid or omni microphone and hold it in front of a kick drum. As you hit the drum, watch the speaker reproduce it and see if it goes in or out. If the phase of the speaker is right, it should move outward. Then make that mic the standard for comparison to all the others you have. Now sit at the board, mute the speakers, and put on headphones. Plug the standard microphone into an input and raise the output so you can hear it right between your ears when you talk into it. Hello, 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 test. There we go. Then mute that microphone, but don't change the levels. Now in another channel, plug in and raise one of the other microphones so that it sounds identical to the level of the first. Hello, test. Test. Yep, got it. Now turn them both on. And talk into both of them right next to one another. Now these two sound hollow and heavily comb filtered, so we know that they're out of phase with each other. If you're correctly hooked up, mic B probably needs to have its polarity switched. Now let's compare another mic to the standard mic. Here's mic C by itself. Now let's turn on the comparison mic. In this case, when they're both on, the sound just gets louder, so we know that they're in phase with one another. If 3 or 4 in a row are wrong, then your standard may be wrong, and you should go back and recheck all the mic cable wires in your kick drum test. There may be a cable, input, or output in the board that's been wired backwards. For checking the cable, use a volt-ohm meter and verify that pin 1 goes to pin 1, 2 goes to 2, and 3 goes to 3. To change the polarity, open up the mic connector, pull it out, and then unsolder pin 2 and 3. Reverse them and resolder. It's important that all your mics have the same polarity so that if they are placed on the same instrument, their combined mono output or stereo compatibility won't have severe phase cancellation.
Omni and cardioid mics have a specific polarity. Ideally, a positive acoustic event should generate a positive going electrical event. But one type of microphone operates a little differently than we've discussed. On a bidirectional microphone, there's no defined polarity. Now, a positive acoustical event on one side of the capsule will generate a positive electrical event. But the same positive acoustical event heard by the other side of the capsule will push the diaphragm in the opposite direction, creating a negative electrical pulse. One side will, in effect, have an opposite positive lobe to the other, which is a negative lobe. Usually the side in which the manufacturer has his logo will be the positive side, but I always test to be certain. Right now, you're hearing the combined outputs of these two bidirectional microphones. Both of them have their positive lobes facing in the same direction. Now I'm going to turn one of them around so that its positive lobe is facing me. Now, if you notice, my voice sounds fairly canceled out. That's because both of the diaphragms are moving in the same direction, but a positive pulse is being created by one of the diaphragms, and an equal but opposite negative pulse is being created by the other. The result is almost no output when the signals are combined. Now, having said all this, There are times when you want to reverse the polarity of a mic because of the way that you're picking up a certain sound. For instance, while I'm not fond of putting a mic under the snare, some people do like to put one below as well as above the snare. As the head of the snare goes downward, the mic above the snare will move outward, but the mic below the snare will respond inwardly. Though they are picking up the same drum, when these two mics are combined, they will seem to be out of phase with each other. The same acoustic event generating similar but opposite electronic signals. In this case, you might get a better combined sound by reversing the polarity of the bottom microphone. Many boards have phase reversal switches. If your board doesn't, make a short cable or small box that reverses pin 2 and 3 on one end. Be sure to label that cord as being out of phase so that you don't trap yourself sometime by accidentally using it. Sometimes when you're doubling the same part in an overdub, a different texture can be created by reversing the polarity on the mic. The result can be a little richer because it is ever so slightly different from the original. Now, we've just seen that cancellation can be caused by combining signals of different polarity. Cancellation can also occur when a direct signal is combined with a delayed or reflected signal. This can happen because a direct signal is being combined with reflections off nearby surfaces or because two mics are at a different distance from a common sound source.
Wavelength is the physical space occupied by one complete cycle of a given frequency. For example, a 1,000 cycle tone has a wavelength of about 1 foot in reality space. If the distances involved between a direct sound and a reflected sound are about the same as the wavelengths of the frequencies being played, the two signals will add and subtract from one another, according to the phase relationships of each frequency present. In this case, the sound bouncing off the wall reaches the mic 1/2 cycle after the direct sound and cancels it out with an equal but opposite pressure. In this example, the microphone is picking up a direct signal from the speaker and a reflected signal from the wall. At certain distances, these two signals will audibly cancel one another. Phase cancellation will be greatest when the delayed signal is half a wavelength after the undelayed signal. In this example, two microphones are picking up 1,000 cycle tone, and you're seeing the combined signal on the scope. Since 1,000 cycle tone has a wavelength of about 1 foot, the greatest cancellation between these two mics occurs when one is 6 inches further from the source. Cancellation of a lesser degree occurs at 1.5 wavelengths of delay, 2.5, and so on, each cancellation creating a dip in the frequency response. This is called comb filtering, because a group of narrow notches form what appears to be a comb in an otherwise flat response curve. Now, not all reflections are bad. Medium reflection times in the Haas zone, 10 to 45 milliseconds, will usually enhance the sound. But if a microphone is placed in a particularly bad spot, which picks up a variety of very short delays, anywhere from 1/10 of a millisecond to 10 milliseconds, it might start sounding filtered and hollow. The shorter the delay, the higher the beginning frequency of cancellation. Moving the mic, the sound source, or any of the acoustic variables will change the frequencies that are affected. In this case, we've moved the guitar and mic a few feet further from the wall. If you combine two or more microphones that are picking up a common sound source, or the mics are near a reflective surface, there will be some comb filtering occurring. It's unavoidable and happens all the time.
It can enhance the sound or destroy it depending on all the variable specifics such as distance, type of mic and patterns, the instruments, and all the acoustical space variables and reflections. If the sound source moves, such as a cymbal when it's struck, the distance between the mics and the cymbal change. This causes the frequency of cancellation to sweep with the swaying cymbal and creates acoustic comb filtering. The pair of overhead mics on the drums are the most likely to experience this problem. You may be able to improve the sound by just moving the mics. Now, if you have a lot of reflective surfaces around the microphones, the problem is more apparent and severe. So if, for instance, you're recording drums in a booth surrounded by glass, the comb filtering will be substantially worse than if the drums are recorded in a large open space. Usually I like to set up the drums in the middle of the studio, and I put the guitar amp in the drum booth. I find most people who design drum booths never played drums. Sweeping phase cancellation is difficult to hear in stereo, but it's more obvious in mono. It's quite a nasty surprise to mix down and go to master, only to discover that there's flanging on the cymbals and that the mix is not monophonically compatible. Once it's on tape, it can't be fixed, so check it before you put it on down. The way to check for comb filtering is after you get level settings and a reasonable stereo balance, on drums for example, take the stereo pair of overheads and all the other mics you're using on the drums and pan them to one speaker. In other words, listen to everything in mono. Then have the drummer hit all the cymbals and drums. If you hear comb filtering in the overheads or any of the other microphones, move one or the other of the overhead mics an inch or two and try it again. If you have two microphones on a piano, you won't necessarily hear phasing, but you will hear a low-frequency hollowness as a result of the cancellation. Occasionally on a given instrument, any pair of mics might sound better electrically out of phase with each other. The acid test is how they combine in mono. Once you've decided on which polarity relationship sounds best, reposition the stereo pair to the left and right for your mix. It's amazing how the apparent center and general imaging will shift by reversing the polarity of one of the mics in a stereo pair.
One solution for phase problems is the pressure zone microphone, or PZM. PZMs are designed to eliminate comb filtering that occurs when a microphone simultaneously picks up direct and reflected sound. PZMs are designed to face and nearly touch a large barrier, like a wall. The bigger the wall the PZM is against, the better the low end. But after 6 or 8 feet square, it doesn't seem to matter that much.
You're now hearing my voice through a conventional microphone about 1.5 feet away from this wall. The direct sound in my voice is combined with the bounce off the barrier. And at certain distances, you can hear the comb filtering. Also, my voice loses distinctness because of the reflections as I rock back and forth. Now you're hearing my voice through the PZM. By eliminating early reflections from the wall, the PZM eliminates comb filtering caused by the differences in sound path distance. PZMs are used when you want to pick up the total room. They're quite non-directional, and they don't work for just picking up one isolated instrument. Everything in the room is going to come through, so if it's a bad-sounding room, the PZM won't work so well. PZMs are very popular anytime you're doing acoustic recording in a very good space. Some people like to put PZMs on the inside of a piano lid, so they can use the lid as the barrier. But PZMs are terrible for PA because their omni patterns make them very prone to feedback.
we've seen two different ways the signals can cancel one another by being out of phase. If two mics have opposite polarity, the signals will cancel. So it's important to check that the polarity of all your mics is correct and the same. Cancellation may also occur when a direct signal is combined with a delayed signal, either because sound is bouncing off some reflective surface, or because two mics are being used at different distances from the same sound source. This comb filtering may be minimized by eliminating reflective surfaces, by changing the spatial relationships of sound source, mics, and walls, or by the use of a pressure zone microphone.
The purpose of stereo miking is to pick up sound from 2 points in space just as your ears do. This is done by recording from two slightly different perspectives using two identical microphones spaced slightly apart. One common approach is to pick up the stereo information by using two microphones angled toward one another and nearly touching. The capsules face the sound at an angle somewhere between 90 and 140 degrees. This is called XY recording. The stereo image is created by the slight difference in intensity and phase between the two microphones. Classical recordings are often done this way. The advantage is that when the two capsules are so close together, there's very little phase cancellation due to the time delay caused by the distance between the two microphones. This kind of recording sounds very real on headphones because the distance between our ears and the distance between the mics is almost the same. When the speakers are spread out, however, the distance between the recording mics is not enough for the playback to be stereophonically dramatic. You can also put a couple of bidirectional microphones on top of one another so that both of their positive lobes are at a 45-degree angle to the sound source, and their negative lobes are facing the rear of the hall to pick up primary reflections. This technique gives a good stereo recording, and many people like this unique placement. This approach is called stereosonic recording. For pop music, most people want a bigger-than-life sound. So most stereo pairs for rock and roll are placed a few feet apart, depending on what instruments are being recorded and how wide you want the stereo separation to be. On a pair of drum overheads, the distance may be 3 or 4 feet between the mics. This kind of separation is called A-B recording, and it gives an expanded stereo impression on separated hi-fi speakers found in most living rooms and cars. On the other hand, on headphones, it makes the sound seem to center at the top of your head. The headphones are trying to tell your ears and brain that your head is 3 feet wide. The fourth way that stereo miking is done is the MS, or mid-side technique. There are mics specifically designed for MS recording, such as this Fostex M22, but most stereo microphones which have selectable patterns and a rotatable head can also be used. The mid-side technique utilizes a cardioid mic facing the sound source and a bidirectional mic at right angles to the sound source. In-phase information from the bidirectional mic is combined with the signal from the cardioid mic to create one stereo channel. Similar out-of-phase information from the bidirectional mic is combined with the cardioid mic to create the other stereo channel. How much side information you bring up will control the width of the stereo image. If you use too much of this side information, the center will swim and the left and right will cancel when combined to mono. This technique is mostly used for classical recording and TV stereo. However, it doesn't give the exaggerated separation that most people want for pop recordings. On the other hand, this approach is excellent and natural sounding for jazz, choirs, and churches. Many people use this technique for stereo drum overheads. This approach has better phase coherency than XY, and if correctly done, has perfect mono compatibility, which is why people in television like it. It's nearly the best you can do for listening on headphones. The absolute best way for making a recording for listening on headphones is to use a dummy head, or get a dummy to let you use his head, and you put lapel microphones in the ears. or use a dummy head stereo microphone system such as this one made by Sennheiser. When you listen on headphones to something that's recorded this way, you're definitely there. We've looked at 4 basic approaches to stereo miking. XY for a naturalistic stereo effect. The stereosonic approach, using 2 bidirectional mics. The AB technique for dramatic stereo separation. And finally, the mid-side technique using cardioid and bidirectional mics in combination. The approach you choose will depend on the kind of music you're recording and, of course, your personal taste. As we have seen, there are lots of factors to consider when it comes to choosing mics for your studio. How does it respond to highs, to lows, to transients? Is it delicate or durable? Does it need a power supply? The importance of each of these answers will depend on how you plan to use a particular mic. Spec sheets can help, but listening is the ultimate test. If you're a singer, for example, the best way to choose your golden slippers is to take a tape of a song you know well to a music store and actually record yourself singing along to the track. Try different microphones until you find the one you like best. You can't tell how well a microphone will perform for recording until you actually record with it and then listen to a playback. It's not like a PA microphone where you can stand in front of the stack and hear what's coming out. Of course, a great vocal mic won't necessarily be great for everything, but it will probably be good for most acoustic work, such as piano, guitar, violin. There are microphones which are not very good for vocals, that are great on drums, for instance. When looking for a microphone, remember that many microphones physically look the same, but actually sound quite dissimilar. For instance, this microphone is much richer and fuller, as opposed to this microphone, which is a more bright and a little bit thinner, more tinny sounding. That's because there's differences in electronics. The acoustic design of the capsules are different. There's differences in the nature of the housing. Now, if you need a lot of mics for live performance, there are many that can be used for both performing and recording. But generally, recording microphones are brighter and don't work as well for live performance because they are prone to feedback. They're too sensitive for close-range vocals and will pop on S's and T's and P's, for instance. So you'll probably have to buy at least a couple of good microphones to be used primarily for recording. Maybe 1 pair, and then add a single mic here and there. If you're not recording live drums, you'll probably never need more than 2 or 3 mics for most sessions. If you are, you'll want at least a pair of bright microphones for your drum overheads and another for the hi-hat. You'll need a good vocal mic, and then 4 or 5 other mics for drums. The drum overhead mics will probably also serve well for acoustic guitar, piano, mixed percussion. Included with this tape is a chart that shows some of my usual choices for specific applications, but you have to decide what sounds best for your particular sound. Now that you've selected your mics, let's talk about some accessory devices. The first of these is the microphone pad. Most microphones are designed so they can generate a very wide range of output before distortion, and generally wider than the dynamic range of most microphone preamps. Sometimes a mic will put out so much signal that the preamp can't be turned down far enough, and the signal from the mic continues to overload the mic preamp. The solution is a microphone pad. A microphone pad introduces a loss to the signal by dropping the microphone's output before it goes into the preamp. Whether or not you use a pad depends on what you're recording, the gain of the preamp, and the output level of the microphone. For a violin or wind chimes, you probably wouldn't use a pad, but for a drum or trumpet, you probably would. Now, many boards have an internal switchable pad, but if your board doesn't, get a few inline pads. These are cigar-shaped tubes with microphone connectors at both ends. You connect them between the microphone cable and the input of the board. You can also get some that are switchable. These, for instance, have 5, 10, and up to 50 dB of switchable pad. Now, condenser microphones also have pads that go between the capsule and the internal preamp to prevent the overload of the mic's built-in amplifier.
Once you've got your mics, you'll need some way to keep them where you want them. The stand is what holds the microphone in position. Be sure to stay away from overly cheap stands. You need ones with good stability. Always give the stand a shake and listen for any rattles. Now, a lot of stands exhibit mechanical sympathetic vibration to foot tapping, bass, or kick drum, for instance. And the fittings, well, the fittings will loosen, so you should always go through and tighten up the bolts and nuts and wobbly wheels so there are no rattles, or otherwise, when you mic a set of drums, the sympathetic rattles in the stand will be picked up by the mic. Now, most mics have some type of internal shock mount to minimize handling noise and stand vibration, but most can also be improved by an external shock mount. The best of them looks like this one, where there are two rings of elastic spider web with the mic suspended in the center of the two webs. However, hardly any of the commercially available shock mounts will stop low-frequency rumble or shock vibration, for instance, foot tapping.
The best way to isolate the microphone and stand is to use a block of mattress-type closed-cell foam rubber, about 2 or 3 feet square and maybe a foot or so thick. Just flop it down on the floor and put the stand up in the middle of the rubber. That way you have a foot of rubber between the stand and any vibration in the floor. Sandbag the base if the stand seems precarious.
The foam can do double duty as an isolation wall between two instruments, and as most musicians will tell you, it's a great place to crash if you can't make it home some night. Now, the quieter the sound that you're recording, the more critical it becomes to isolate the microphones. Some people, in fact, hang their drum mics from the ceiling to prevent vibration. And yes, if the ceiling moves, a certain amount of vibration will go down the cords. Another thing, many times the transient response is hurt by a windscreen on a PA-type vocal mic. If you're only buying one microphone to be used for both PA and recording, get one that allows you to remove the windscreen. Like this. Take it off for recording and leave it on when you're using it for PA. Manufacturers usually claim that the windscreen doesn't affect the sound, but I've never found that to be true. While recording, you shouldn't have to worry about popping P's or T's, since you should be working farther away from the microphone. When you get further away, you don't have a problem with either of those. Sometimes raising or tipping the microphone away from the direct axis of the sound will also minimize the percussive S's and T sounds. For instance, if I take and tip the microphone so that I'm now talking or singing across the top of it, I eliminate a lot of those problems. Sometimes the mic will sound like it's being popped or blown into just because the sound close to the mic is so percussive, like a shaker or a pair of maracas, which have such a high pressure transient that moving them back and forth close to the mic will make it sound as though it's being hit. Just pull the mic back from the instrument a bit, or vice versa. When you really do need a windscreen, the best ones are made of pantyhose stretched over a 4-inch loop at the end of a straightened coat hanger. You take the loop and you position it about 2 or 3 inches in front of the mic. That's an old trick some engineers have been doing for years. But now you can even buy them ready-made. They maintain the high-frequency clarity, and yet they block the percussive wind turbulence like S's and T's or P's. The right selection of mics and accessories is a highly individual matter. When it comes to mics, it's important to try them out and to choose mics that are really appropriate for the kind of recording you plan to do. As for accessories, get what you need to help your mic sound their very best. Is this the shot for the Rolling Stone interview?
Yes.
Oh, okay. Well, believe it or not, we're finally ready to get down to using microphones. Choosing the right mic for each specific job and determining the position of the mics in relationship to the sound source. Now, up to now, mic description has been reasonably objective,
But now we're moving into that murky realm of the subjective. There's always exceptions and things that just happen to work for you and no one else. The best attitude is to be flexible and willing to try things out.
Microphones are brushes. You use them to pick up the sound colors and apply them onto your canvas. Or to put it another way, they are the windows through which we observe the sound. Each instrument's essence, which is what you're trying to enhance, lies in a different range. You want to select the mic that brings out the desired best view of each source. It's much like using different brushes to blend the brush strokes of a painting. Mic placement depends on the instrument or voice you're trying to record and the sounds you want to capture. The closer you are to the source, the more of a specific point you'll pick up. The further back you get from it, the more open and natural the sound will become. The more you pick up the overtones, overall timbre textures of the source, and the environment. An even blend of the stereo panorama in the acoustic field is lost if the mics are too close to the source, and certain points in the sound will stick out. At the other extreme, placing the mics too far back will give all reverb and a loss of clarity and definition.
Let's look at some ways of miking some specific instruments: drums, guitars, pianos, ensemble sounds, and vocals. Let's start with drums. There are thousands of ways to mic drums and percussion sounds, but by and large, most people use one of three approaches. For mono drums, the simplest is to use one overhead mic on the whole drum kit, augmented with one kick drum mic and one on the snare. You should use a small diaphragm condenser or some other bright and compliant mic for the overhead. Maybe a small diaphragm dynamic on the snare. For the kick drum, more than likely a large diaphragm dynamic. A dynamic microphone like a Shure SM58 has a diaphragm with a relatively large mass that is reasonably non-compliant. It tends to not pick up high frequencies very well and slows down a percussive transient. Now this can be used to your advantage if you want to get a little bit of acoustic compression on the drums. For instance, if you're using an SM58 on tom-tom or kick, it will compress the attack of the stick or beater, thus bringing out the sustain and fatness of the drums. If the hi-hat part's very important, you might use an additional bright-sounding mic on it to get that close attack sound. Another way to get a good drum sound would be to put one on the kick, one on the snare, an additional microphone on the hi-hat, and a pair of overheads. Pan the first two mics to the center, and pan the overheads to left and right. Pan the hi-hat to the side shared by the hi-hat overhead. On multitrack, the way most people record organic as opposed to triggered or electronic drums is to put one microphone on every tom-tom, one on the kick, one on the snare, one on the hi-hat, and a pair of overheads. If the drummer has a dozen toms, I usually use a bidirectional mic positioned between each pair of the toms. But make sure their polarity lobes are all facing in the same direction. If the drum heads have dents all over the place, the drummer's a flailer and will probably hit any mic within stick reach. In this case, the word to the wise is, don't close mic, and don't use your best mics. The subject of tuning and setting up drums for recording is a discussion on its own, and we'll cover it in another tape. For now, I'll just mention that to get a good drum sound, it's important for the drummer to remember that he or she is recording and not playing live. Guys who play live hit the drums hard, but they hit the cymbals even harder. Drummers who record have to hit the drums hard and the cymbals much lighter, or else all the microphones pick up is cymbal wash, which clouds everything. Also, if it can be avoided, don't put the drums in a small booth because it creates phase problems, as we showed earlier. and make sure the floor under them doesn't move. I usually like a hardwood floor with a small rug between the kick drum and the hi-hat and throne. Basically, a great drum sound starts with a great sounding set of drums and a drummer that can play them well. If they say the drums sound like cardboard boxes, go and take a listen. Maybe they really do. A lot of acoustic guitars have pickups, and many people will use them for recording. It will sound like an electric acoustic, and that's fine if that's what you want, but it's not really an acoustic sound. To get a good acoustic guitar sound, you first need a decent sounding guitar, new strings, someone who can tune it up, and of course, someone who can play it well. I always set the player up on a hardwood floor or put down plywood over the carpet between the player and the mics. If the player is sitting, make sure the chair doesn't have any arms and doesn't squeak. Also make sure there's no tapping or button rattling from jewelry that can also get picked up. If you're recording a mono track like basic rhythm guitar, one microphone will probably do. Use a bright, compliant microphone with a fair amount of output, probably a condenser or one of the high-output ribbons. You want to be able to hear the life of the guitar, its brilliance, its overtones. Pull the mic back to about 2 or 3 feet from where the guitarist is playing and face it in the direction of the guitar. Move it around using a bit of trial and error until it sounds exactly the way you want to hear it. Some people combine a near mic with a distant one to create a certain amount of acoustic interaction. If the guitar is a featured instrument, you probably want to record it in stereo. Have the pair about 2.5 to 3 feet away and separated by 3 or 4 feet. Keep in mind that the focus of the sound comes from a specific area of the instrument, but it's the entire body that radiates overtones, harmonics, and timbre. The instrument needs to interact with a compatible acoustic environment. In other words, a good room. Sticking a mic right into the sound hole just gives you rumble and mud, a lot of finger noise. And besides, who do you know that listens to a guitar with their ear in the F-hole? For electric guitar amps, the mic should be back 1 to 3 feet. Often, I put a reflective surface on the floor between the amp and the microphone so that I get some short, early reflections off the floor that enrich the overall sound. Usually, I prefer to put the amp on a large rubber block so the mics are in direct line with the speakers, about a foot or so off the floor. Also, the guitar amp is physically decoupled from the studio. If you want a closer sound, pull the mics in. If you want a more distant sound, pull them back. When it comes to electric guitar string noise, many players love those sounds as their fingers scrape along the strings. It gives the impression that the guitar is at a screaming loud feedback level, and that flames are leaping off the player's fingers. Several times I've ended up recording a track of just finger noises and string slides. Later I blend in as much of that as I want. Most of the time it does make the guitar part sound more exciting and provides a sense of anticipation to the beginning of the solo. One more variation is to run a Rockman into a small powered speaker and mic the speaker. If you need feedback, put the small speaker on a stool right next to where you're seated, so that the speaker blasts right into the pickups. This way you can get pickup feedback and big amp sustain without shaking the building apart. You can either mic the little speaker or run out of the Rockman direct and just use the speaker for feedback. If you're going for an ensemble sound, you can take one bidirectional microphone and put it between a pair of horns. Or put a wide cardioid in front of 3 horns of the same type and voicing. Usually the best way to record horns and strings is to use a smaller, tighter section and have them double their parts. This means playing and recording the same chart 2 or 3 times on different tracks. Rather than try to record them in stereo, take these 2 or 3 mono tracks and pan them left, center, and right. By miking the horns at some distance, the overall sound will open up like a jazz band horn section, as opposed to a more rock and roll type horn section. Rock and roll horns usually use close miking, close to the point of being stuck right in the bell of the horn. One mic goes on each horn, and all the mics are mixed together onto 1 or 2 tracks. If you're going for a solo sound on sax, flute, or trumpet, I would pull the microphone back and open it up a little bit. I'll usually mic and record a solo instrument in stereo. Usually you'll use a fairly bright microphone, but the lower the horn or string range, the bigger the diaphragm should be. All the early Tijuana brass recordings were mic'd at a distance with a long ribbon microphone, which are the faves for many horn players. Generally, I'll use a smaller diaphragm mic for trumpets, high reeds, and strings, and a larger diaphragm for trombones, lower saxes, cellos, and string bass. When you blend the different horns or strings into an ensemble, it's usually a good idea to favor the low-end register, the baritone or cello and so on, even more than they might seem to need. Otherwise, when the strings or horns are balanced in with the final mix, the low voicing will seem to flatten out and tend to get lost in the mix. With a horn section, I'll let them set up in a line with the first trumpet on one side, then the second trumpet, then the trombones, and the saxes at the other end. If the saxophonists are also playing flute, I'll set up a second set of mics that get turned on when they do the flute parts, since the placement of the mics for these 2 different types of reed instruments is so different. When they're playing sax, the mic will be low, and when they switch to the flute, it should be up high where their lips are. Again, if you're going for a solo open sound, pull the mics back. With violins, violas, cellos, and string basses, trying to get them to sound good with close miking rarely works. And besides that, they'll keep hitting the mics with their bows. Most of the time, you'll pull the string mics back to get an open, full sound. Trying to record strings in the same room where you have anything else going on is next to impossible, because the pulled-back violin microphones will pick up everything. They need to be in a live and open space. In a dead room, not only will they sound bad, but the players will hate it. If I'm doubling a string section, I'll usually go out and move the mics a little bit for each overdub, or reverse the relative polarity of all the mics. It gives just enough variation to enrich and add a difference to each section. For an electric sound on violins, I would definitely not use a contact mic. A contact mic on an acoustic instrument just doesn't sound right, particularly on violins, and frankly, most violin players flip out when you even suggest attaching anything to their prized possession. Instead, I'll put a mic on the instrument and plug the mic into a guitar amp, which is in the vocal booth or isolation room. Then I'll mic the amplifier. I've used similar setups on piano, brass, many other instruments. With a grand piano, I generally pull the lid off for pop or rock recordings. If you don't take the lid off, the sound hits the lid and then bounces right back into the microphones. The lid on the piano was mostly designed to project the sound into a concert hall. But for recording, you want the sound to go out and then go away. Usually I'll put two microphones right above the hammers, because most of the time I want that very percussive sound. I'll put the mics as close as 9 inches to a foot from the hammers and spread them out about 2 to 2.5 feet apart, depending on the range that's being played. If you want to sound less percussive, then raise the microphones. If you want to get more low end or sustain, put one mic up near the high hammers and move the second one down to the harp of the instrument, about the 3rd or 4th hole in the harp. For most piano recordings, you want to go with very bright, compliant microphones. Contact mics just don't work that well on acoustic pianos. But for a little bit different sound, a lot of people have good results with PZM mics, attached to the inside of the open lid. If you're doing a concert-type acoustic, leave the lid on, but open it up full. Pull the microphones back. To decide which stereo setup to use, A, B, X, Y, or mid-side, refer back to the earlier section of this video. I prefer the A-B approach using 2 omnidirectional microphones, one to the back of the piano, one at about 30 degrees angle to the keyboard and facing the piano's opening. Both mics should be about 10 feet from the instrument. To really get a big classical sound, you need a large live room and a great player, of course. We've seen that each instrument requires a different miking approach, but there are some general principles that apply to all situations. You want to choose microphones that are appropriate to the frequency range of the instrument. And generally, you will want to choose a placement that's far enough from the instrument to bring out the overall texture of the instrument and the response of its reverberant environment. But you don't want to be too far back so that you only pick up reverb. Extremely close miking is only appropriate when you want to isolate a specific aspect of an instrument's sound. You may need to adjust the environment with plywood panels, foam blocks, or blankets to get the sound exactly the way you want to hear it. And nothing is more important than having a fine-sounding instrument in the hands of someone who knows how to play it. Last but not least, let's talk about miking vocals. Usually you want to place the mic a foot or so in front of the singer. Some singers, they love to have their lips right up against the mic. If a singer keeps eating the mic, they probably need to hear more of themselves in their headphones. If they keep stepping back, they probably are hearing too much. In fact, if they're moving around at all, calm them down and put an X on the floor to mark the spot. For background vocals, I'll often have 2 voices singing into a single bidirectional microphone. For more than 2 voices, an omni pattern is best. The idea is to have everyone get their natural blend around one microphone. This is how almost all professional backup groups do it. Using separate mics and mixing them together doesn't really cut it. It doesn't really get the blend. Usually the background vocalists will take off one headphone so they can hear everyone else and themselves better. Then it's easy. Them that are loud steps back and them that are quiet moves up. Get a box for them that are too short and put a rug under everybody else. Also, have the toe tappers remove their shoes and all rattling jewelry gets taken off. Finally, if you decide to change mics on a vocalist, or for that matter anything else like headphones, reverb, or the color of the wallpaper, you better have a good reason. Because if the magic is flowing, you don't want to tinker with its influence. Singers who have been at it a great long while tend to become comfortable with a certain type of mic, and that's what they want to hear. I recall putting up one of these old magical microphones up in front of a singer many years ago. After he listened to playback, he said, "No, that's just not me." So he went digging around in a big box of cords and power supplies and so on, and after a few minutes he came up with this funky old microphone that looked like it had been run over by a truck. We plugged it in, and he gave his all. That was his sound. The right microphone is whatever gives the singer that special feeling down to the tips of their toes inside those golden slippers. To come full circle, every microphone is unique. Each of them has a certain sound that makes the best choice on a given day. And all are only as good as the sound that enters them.